So today we are going to discuss simple stress and strain, axial loading, transfer loading, generalized Hooke's law, and elastic constants. Yes, am I audible? Okay, okay. So we are going to discuss stress strain in a compound axial loaded member, stress strain in a parallel composite axial loaded member, and generalized Hooke's law and elastic constant. Okay. So already you studied this stress and strain. Stress is nothing but the resistive force per unit cross section area, and strain means it, it is the change in dimension to the original dimension. It's a measure of a deformation. Okay. Now compound member, whenever we connect two or more than two members of a different cross section, or simply if we connected more than two members with the same cross section, then it is known as a compound system. And composite system, whenever we connect two or more than two members with a different material, then it is known as a composite system. So there are the compound composite systems, maybe in a series or maybe in a parallel system. Okay. Now first we'll see Hooke's law. So stress is a directly proportional strain within elastic limit. So by experimentally, it is found that stress is a directly proportional to strain within the elastic limit. Means we can say sigma is directly proportional to the small e. So E equal to means this Young's modulus of rigidity equal to sigma by small e, but sigma equal to force by area, and E equal to change in dimension to the original dimensions, E equal to delta L by E. If we solve this, we will get here E equal to PL by A into delta L, and finally we get equation delta L equal to PL by E. So if we know the force, applied force, length of a bar, area of cross section, and Young's modulus, we can find out the deformation of a bar. Cross section, we can take cross section, any cross section. This formula is applicable within elastic limit. Okay, delta L equal to PL by A to find out the deformation. Now we'll see stress and strain in a compound member. Here you can see two members connected together. Material of two members is the same. So Young's modulus, that value of E, capital E, is the same for both material, and length of first member is different, length of second member is different. Let area of a member AB is A1, member BC is a A2. Now stress in AB. So to find out the stress, we need to find out the internal force. So to find out the internal force, we need to break the system. So we break the system here. We break the system randomly between A and B, that if we break the system, it divide into two parts. This P force goes in the left part, and this another at the extreme right. This part is go in the right side. Okay. Now this internal force, we need to find out the internal force. Let this force is a PAB. We don't know the magnitude and direction of this internal force, but here we assume that that force is a tensile and magnitude is a P. Okay. Now stress in a member AB equal to sigma AB, or we can write here P divided by area of cross section of a member AB. Stress in a member BC equal to P divided by A2, right? Now to find out the force in the member BC, we break the system again in between this BC, okay, and we draw here free body diagram. But this system is in equilibrium condition. This system is equilibrium condition means we can say summation fx equal to 0, summation fy equal to 0, and summation of movement of all forces about any point equal to 0. So by using that condition, if we apply summation fx equal to 0, this P force is acting at the surface A, right? And this PAB acting that is the internal force. If we solve for the summation fx equal to 0, we'll get the value of PAB. So PAB equal to P. So due to that, here I have written stress in a member AB equal to P by A1. Okay. And similarly, we can find out the value of PBC. That force in a member BC, that is the internal force. Okay. Again, I break the system in between this B and C. Randomly, I break the system. Then I have drawn here free body diagram. This and applying a summation fx equal to 0. Treat rightward positive, leftward negative. In this way, we'll get the value of PBC equal to P. So stress in a member BC equal to P by A2. Okay. Now material is the same, so we can take E is the Young models for the steel material, and strain. To find out the strain, we know the formula for the Young's modulus according to the Hooke's law, E equal to sigma by E. So we can write here strain in a member AB equal to stress in a member AB divided by Young's modulus. Just interchanging a term of this formula. So EBC equal to sigma BC divided by E. Now total deformation. Now here we are applying the force at the end of the two members, at the left side or right side. Due to that, this steel member is going to elongate. This another second member BC is also steel. That member is also going to elongate, right? But we can see here cross section is larger of this second member BC compared to member 1, right? So this member going to more elongate compared to BC member. But how to find? Here we can take total deformation. How we can find out the total deformation? Total deformation equal to delta L equal to delta L1, deformation of member first plus deformation of member second. But we know that formula for the deformation. Already we have seen the formula for deformation, that is delta L equal to PL by AE, right? So just I replace or I use this formula to find out the deformation of member first and member second. So in member first, delta L1 equal to PL1 divided by A1E. This L1 because length of first member is different and area of first member is different. Similarly, we can calculate the by using we can calculate delta L2 by using formula PL by AE. Delta L2 equal to PL2 by A2E. Then total deformation. Now put the value of delta L1, delta L2 in this equation. So we'll get delta L equal to P by E into L1 by A1 plus L2 by A2. Okay. So in this way we can calculate the deformation whenever members are in a series. This member may be having the same material, this member may be having a different material, or this member may be having different cross section, right? So if we know the basic equation, that is delta L equal to PL by A, we can solve the problem. Okay. If member is in a series and with a different material or same material, we can solve the problem. Now we'll see one problem. Now we'll see how to solve the problem. A bar of uniform cross section 100 mm square. So cross section of bar is given. Your cross section of all three bar is equal. That is 100 mm square is subjected to force as shown in figure. Is subjected to force as shown in figure. Calculate the change in length of a bar. Means we need to find out the total deformation. Take E equal to 200 GPa. Means Young's modulus of material is given 200 GPa. Draw axial force diagram. Okay. Now this diagram is given to you. So here you can see there are the three members. This first member is a sky blue, second green, and third is a yellow. And intermediate forces on this member system is given. This all load is a axial load only, right? And we can say this is an axial load in member system because load acting at on the axis only. Okay. So just I have given the name A, B, B, C, and CD member. Okay. Length of first member is 300 mm, each already given. Length of second member is 400 mm. Length of third member is 600 mm. I will see how to solve it. So I have drawn this figure once again. Now we know that basic formula is delta L equal to PL by E. But here three members connected together. So we need to find out the deformation of each member. Then we will add deformation of each member. Because length of each member is a different. So we will get the deformation, different deformation. Area of cross section is the same. But you can see here delta L equal to PL by A. This delta L deformation is depends on the length also, right? So we need to calculate the deformation of each and every member. So formula is for this delta L equal to delta L1 plus delta L2 plus delta L3. Okay. Now first we'll find out the delta L. Delta L1, we are using formula PL by A. Just I have written formula in terms of a member. That force in a member AB, length of member AB divided by area of member AB into Young's modulus. Okay. Now to find out the internal force, we need to break the system because this is the external force. To find out the force in the member AB, we need to break the system. So I have break the system here in between AB, and this is the left part of the system and this is the right part of the system. We can consider any part, either left part or right part of the system, but just check that in which part number of forces are less to avoid the confusion. Okay, to avoid the calculations. So here I have taken a left part only. Now apply equilibrium condition, summation fx equal to 0, right? Treat rightward forces positive, leftward forces negative. But in this case, this 1 kilonewton is acting rightward, and this PAB, this is the assumed direction, and this PAB is a unknown force, internal unknown force. So generally assume this force tensile force. Okay, if we get the answer negative, then that means that force is a compressive force, internal force is a compressive force, and that member trying to compress the member. Okay, so summation fx equal to 0. Why we are applying summation fx equal to 0? Because these all forces are acting in a x direction, and this system is in equilibrium. So we can apply equilibrium condition if we break the system in any number of parts. If system is in equilibrium, then all parts also in equilibrium, right? So here we can apply summation fx equal to 0. by using sign convention, we will get PAB plus 1 equal to 0. So finally we will get PAB equal to minus 1 kilonewton, right? So PAB equal to minus 1 kilonewton means here is the compressive force, but you need not to change the sign for further calculation. Okay. Now we'll see second member. Again, I have drawn the same system, but to find out the force in a member BC, I broke the system here. Now this section line divide the system into two parts. This is the left part and this is the right part. Okay, but we can consider any part as per our convenience. Just treat rightward forces positive, leftward forces positive. Again, this PBC member, force in a member BC, this is the internal force we need to show here. Okay, and this PBC member is take always tensile to avoid the confusion. Okay, for convenience purpose, this take always tensile. Now I will apply equilibrium condition, summation of x equal to 0, PBC plus 1 minus 3 equal to 0. Here in this diagram there are the three forces, two forces acting rightward, one force acting in a leftward. So PBC plus 1 minus 3 equal to 0. So PBC equal to 2 kilonewton. Value of PBC is a positive here, right? Now if we solve the right part, again we will get the same answer. So that PBC equal to 2 kilonewton. Now we'll solve for the third member, that is CD member. Again we need to break the system into two parts. So I have taken here section, cut section, and now for this I have considered the right part, because in right part there is only one force. Okay, so and that force is acting in a leftward, and this is the internal member, internal force of a CD member. Here I have taken tensile. Again use the equilibrium condition, apply sign convention. So we'll get the PBC force, that is internal force in a member BC, equal to minus 2 kilonewton. Means it's a this force is a compressive force. Okay, so in this way, first we need to find out the internal forces in the system, then we need to find out the deformation of each force, each member, sorry, by using equation delta L1 delta L equal to PL by AE. So basic equation delta L equal to PL by E. Now here I have calculated delta L1, delta L2 and delta L3. Delta L1 formula is PAB LAB divided by AB into E. Okay, so just putting the value, value is 1 kilonewton, so I have written here 1 into 1000 to convert kilonewton into Newton. Then length of AB is given in mm, divided by area of AB. Area of AB is given 100 mm square, and Young's modulus value is given 200 MPa, means 200 into 10 raised to 3. So in this way, delta L1 equal to minus 0.015. Minus because here is the compressive force. We get PAB value is minus 1 kilonewton. Then similarly, we can calculate the value of deformation for the member BC. So use formula delta L2 equal to PAB LAB divided by AB into E. Okay, so here we'll get the value 0.04 mm, and delta L3 again using basic equation delta L equal to PL by AE, but we need to take force in a member AB, that force in a member, sorry, force in a member CD. Here force in a member CD, length of a member CD, area of a member CD. Here length of a member BC, length of a area of BC. Okay, so in this way we'll get the value of delta L1, delta L2 and delta L3. Okay, if we do the calculation, if we add all the deformation, we'll get the total deformation, and the value of total deformation is a 0.035 mm. So in this way, just simple calculation we need to do to find out the deformation in a compound member system. So here just if Instead of steel, if they use a copper material, we can use a Young's models of copper material, but this procedure will remain same, and system will be composite system. If we connect two or more than two different material together, then that system is known as a composite system. Okay, so in this way we can find out the deformation. Do you understood how to calculate the deformation whenever system is in a series, whether compound system or a composite system? Compound system means only two or more than two members connected together. Okay, composite means whenever two or more than two different materials members connected together. Do you understood? Yes. Okay, now we'll see composite system. Composite parallel system, this is related to whenever members connected in a series. Now we'll see composite system, stress and strain in a composite parallel system. Once again I will repeat, a composite system may be defined as bar made up of a two or more different material joined together in a such a manner that the system extends or contracts as a one unit equally when subjected to tension or compression. Here you can see these two bars suspended from the roof, and material of this system is different. This first member is different, and material of second member is also different, and we have applied load combinedly. Then we'll see what is the value of stress and strain whenever system members are in a parallel. The more important thing, that assumption is the extension or construction of the bar is being equal. That is the main assumption for the whenever system is a composite and in a parallel. Okay, members are in a parallel. That is the assumption, the extension contraction. Suppose if here we use a steel material, here rubber material. Obviously rubber material is going to extend more, but we connect this material together in a such a way that deformation of these two material we get equal deformation, right? So then means this is the basic of a composite member. So this is the assumption for the composite member, right? The total external load on the bar is equal to the sum of the load carried by the different materials. Okay, means suppose this is the steel bar, this is the rubber material. Okay, and we applied the load P. So load taken by the member first is a P1, and load taken by the second member is a different. This we are applying this P load means it's not mean like that this half load, that's P by 2 load taken by the first member and P by 2 load taken by the second member. That another important of this composite parallel system. Now we'll go through this derivation. Let P1 be the load shared by the bar 1 out of this total P load, and P2 be the load shared by the bar 2 out of this P load. Okay, then P equal to P1 by P2. This is the total load, and that total load shared by the member first and member 2. So we can say directly P equal to P1 by P1 plus P2. But if we write in terms of a sigma, we know that sigma equal to P by A. So P equal to sigma 1 into A1 and P2 equal to sigma 2 into A2. Let this equation be equation number 1. Now delta L is an increase in the length of a bar. We are applying the force means definitely there will be a change in a length. Okay, change in the length or this bar going to extend. But assumption, strain must be equal in a parallel composite bar. Okay, so means we need to select dimension of members in a such a way that if we apply the force, then elongation of a both bar should be same. So according to that assumption, E1 equal to means deformation, strain equal to by Young's model's formula, E1 equal to sigma 1 by capital E1 and E2 equal to sigma 2 by capital E2. But according to this assumption, strain is the same, deformation is the same, E1 equal to E2. Then if E1 equal to E2, then we can say sigma 1 by E1 equal to sigma 2 by E2, right? And in this way we will get sigma 1 equal to E1 by E2 into sigma 2. So this is the equation number 2. So by these two equations, we can easily find out the stress and strain. But we need to understand these two equations. This P equal to sigma 1 A1 plus sigma 2 A2 and sigma 1 equal to E1 by E2 into sigma 2. I will solve one problem on the concept of this composite parallel system. Okay. A reinforced concrete section of a 500 by 500 mm carries 4 reinforcement bar of a 25 mm diameter. Okay. The column carries load of 1000 kilonewton. Find the stresses in the concrete and steel bars. Take EST equal to means Young's modulus of steel material equal to 210 GPa and Young's modulus of concrete material equal to 14 GPa. Okay. So this is the first we need to convert statement into diagram. This is the concrete block, concrete column. So here I have drawn a column. This column having a specific length, and this is the cross section of a column. So this concrete is of 500 by 500, and inside that concrete, these 4 equally spaced round bar given, right? And diameter of round bar is 25 mm. Okay. Now we need to find out the stress in a steel member and stress in a concrete. So this is the composite parallel system because we have grouted this steel bar in the concrete. Now given load is a 1000 kilonewton and load applied is a compressive load 1000 kilonewton. Steel member Young modulus is given 210 GPa. Concrete material Young modulus is 14 GPa. Cross section of a concrete is a 500 by 500, means it's a square concrete, right? Now to solve this, to find out the stresses in both member, the system is a composite parallel. So first, whatever load, that load is distributed in a 2 members. So we can say P equal to P1 plus P2. First statement, first equation is a P equal to P1 plus P2. That is P equal to, then replace P1 and P2 by stresses sigma 1 and sigma 2. The P equal to sigma 1 A1, because we know that P equal, that sigma equal to P by A. Sigma equal to P by A. So we can say P equal to sigma into A. So just by replacing P1 by sigma 1 into A1 and P2 by sigma 2 A2. Okay. Then P equal to, value of P is given 1000 kilonewton. 1000 into 10 raised to 3. To convert it into Newton. Okay. Then equal to sigma ST. We have taken member 1 as a steel member and member 2 as a concrete member. Okay. Sigma ST into AST plus sigma concrete into A concrete, right? Now P equal to 1000 into 10 raised to 3 sigma st, area of steel equal to 4 into pi by 4 into 25 square. Now this steel member, diameter of steel member is given here, 4 steel members, and diameter of each member is 25. So cross section total area of this 4 member, so 1 2 3 4, so 4 into cross section area of one member, that is pi by 4 into 25 square, plus concrete stress into area of concrete member. Now area of concrete member, to calculate the area of concrete member, we know that this total block, this composite block having a dimension 500 by 500, right? But we need to minus area of this steel bar. So 500 by 500 minus 4 into pi by 4 into 25 square to calculate the area of a concrete. So in this way we will get the figure 248037 mm square, right? Now if in this way we will get the equation 1 in terms of sigma st and sigma concrete. Then second equation, that is basic assumption of a composite parallel system. The strain is the same, so we can say E1 equal to E2, or just replacing this E1 by sigma 1 by E1 equal to sigma 2 by E2. Okay, so we'll get equation sigma st, because for first member we have taken as a steel member, second member we have taken concrete member. Sigma st by ast equal to sigma concrete by E concrete. Okay, so finally we'll get the equation sigma st equal to E concrete, E steel divided by E concrete into sigma concrete. And we know the value of EST and E concrete. Value of EST is 210, value of E concrete is a 14. So we will get the relation between the stress in a steel member and stress in a concrete member. So this is the relation, sigma steel equal to 15 into sigma concrete. Now put this relation, value of sigma st, in the equation number 1, 15 cr. Okay, so if we put the equation 2 in equation 1, we'll get the value for the sigma concrete, that is 3.6 MPa. And if we put this sigma concrete value in equation 2, again in equation 2, sigma est equal to 15 into sigma concrete, will get the value of sigma steel. Okay, so to solve the problem of a composite parallel system, we need to remind these two formulas. First one is a P equal to P1 plus P2, and replace that P1, P2 in terms of a sigma. And second is strain of both member. If there are the 2 member, 3 member, then we need to use E1 equal to E2 equal to E3. Okay, so in this way we can solve the problem of composite parallel system. I hope you understood the concept of composite parallel system. Do you understood? If anybody having doubt, please ask. Okay, now we'll see generalized Hooke's law, or whenever system is loaded in all direction, that okay, this is the 3-dimensional body. Uniaxial loading means whenever force applied in one direction, and this then that system is known as a uniaxial loading. Biaxial loading means whenever force applied in a 2 direction, any 2 perpendicular directions, maybe in x y direction, in y z direction, or in a z x direction, then that system is known as a biaxial loading. And triaxial loading means whenever load is applied in a three direction. Okay, this is known as a triaxial loading. Now we'll see how to solve the problems on a triaxial loading system. So here this block is given. Length of a block is a L, breadth is a B, and T is the thickness of a block. Let P be the force applied in a X direction, Q be the force in a Y direction, and in a Z direction there is a R force, right? Okay. These all forces we assume here are the tensile forces. Then stresses due to these all forces. Now just we'll see stresses in all direction. Stress in X direction. Stress in X direction due to the force P, that is sigma X equal to P by A, because force P acting in X direction. According to definition of stress equal to force by area. So here force by area, and for stress in X direction, area will be B into T. B into T. Okay. Now in a Y direction, stress in a Y direction, sigma Y equal to Q by A. Q by A. Stress in a Y direction. This is the Y direction. Sigma Y. Sigma Y equal to Q by A. Q is the force, and area for the Y direction. Area for the Y direction. L into B. L into B. Because we should always take a cross section area. This force is a perpendicular to this area, right? So area is a length into breadth. Okay, and stress in a Z direction equal to sigma Z equal to R by A. R is the force which is acting in a Z direction, and cross section area is L into T. L into T. Okay, so in this way we can calculate the stress. Now strain is important. Again, we need to consider strain in all direction, strain in the X direction, strain in the Y direction, strain in the Z direction. Okay, strain means nothing but deformation. Okay, due to sigma X. Now we'll see. Focus on only X direction. Now, due to this force P, or indirectly we are saying here strain due to the stress in X direction, that is sigma X, that is P by A. Okay, so in X direction we know the formula for the Young's modulus E equal to sigma by E. So sigma X equal to, in X direction we can say sigma X by EX. So EX equal to strain in X direction, EX equal to sigma X by E. Just in terms of E, EX equal to strain in X direction equal to EX equal to sigma X by E, right? But whenever we apply the force in a X direction, Y direction dimension is going to reduce, and Z direction dimension also going to reduce, because we are applying tensile force in one direction. This other two perpendicular dimension get reduced, right? So get reduced means there is a change in dimension. So we need to calculate strain in a Y direction and Z direction. So strain in a Y direction due to force in X direction. That is, now you can see lateral strain, Poisson's ratio. Poisson's ratio means lateral strain divided by linear strain. Linear strain means when we measure the deformation in an applied direction, then it is called as a linear strain. And lateral strain means when we measure the deformation in a perpendicular direction, means we are applying the force in the X direction and we are measuring the change in the thickness. That is known as a lateral strain. And linear strain means we are applying the force in the X direction, means in a left direction, and we are measuring the change in dimension, that is change in length in a X direction only. Okay, then it is known as a linear strain. And that Poisson's ratio equal to lateral strain divided by linear strain, and this value is always negative. Why negative? Because if we applied force in X direction, tensile force in X direction, Due to that, there will be a change in length, and that change in length will be positive. Or we can say that there will be a extensional length. If length is increasing, we treat that deformation is a positive. If length is decreasing, we treat that deformation is a negative. So if we are applying the force in one direction, and if we found that change in length is a positive, then that strain is a positive. But if due to application of force in that direction, in other direction dimensions goes to decrease. So due to that, here mu equal to minus ey divided by ex. Mu equal to lateral strain. Lateral, now for particular case, in y direction is a lateral strain, and in s direction linear strain. Okay. Or similarly, we can write mu equal to minus Ez divided by Ex. So, okay. Now, strain in y direction. Strain in y direction, Ey equal to minus mu into Ex. Minus mu into Ex. Just we know that strain in x direction, Ex equal to sigma x by E, but this is the linear strain, right? And if we put the value of linear strain, that is sigma x by E here, okay? Or if we put just mu equal to lateral strain minus E by Ex, and we know that value of Ex is sigma x by E. So here we'll get Ey equal to minus mu into sigma x by E. Ey equal to minus mu into Ex. Sorry. Here we can write minus mu into sigma x by E. Sigma x by E, capital E. Similarly, in z direction, this is our z direction. So in z direction, strain due to the force applied due to the stress in the x direction. We are applying tensile force. If we are applying tensile force at that time, this braid Okay. Am I audible?
Yes, sir.
Yeah. Okay. Okay. Now here you can see stress in a z direction. Stress in a z direction, sorry, strain in a z direction due to the stress in a x direction. We are applying the force in a x direction, but due to application of this force, this width, that width b is going to decrease, right? So means we need to take we need to consider strain in a z direction also. So strain in a z direction. Now again we are using same formula of a Poisson's ratio, mu equal to lateral strain divided by linear strain. So in this case, when we apply force in x direction, strain we are measuring the deformation in z direction, means we are measuring lateral strain. So lateral strain divided by linear strain. So we can use here mu equal to minus Ez divided by Ex. So we can write Ez equal to, means strain in a z direction equal to minus mu into strain in a x direction. So due to that, here I have written Ez equal to minus mu into Ex. Okay. Similarly, we can write here minus mu into sigma x E. Okay. Now, strain due to force applied in a y direction. Force applied in a y direction. If we apply the force, there will be a stress. So here I have written due to sigma y. Actually, meaning of this due to force applied in a y direction. Okay. Now strain in x direction, strain in a y direction, or strain in a z direction. Strain in x direction due to the sigma y. So again, we are applying the force. Now forget about the x direction force and z direction force. Just concentrate on the force applied in a y direction. Okay. So force, if we apply the force in a y direction, this thickness is going to increase. Thickness is going to increase. But at the same time, due to this applied force, this length and breadth is going to decrease. Means we can say in x direction there is a lateral strain, and in z direction there is a lateral strain, and in a y direction there is a linear strain. So you can see here in a y direction I have written strain Ey equal to sigma y by E. Ey equal to sigma y by E. Similar, just using the basic formula, capital E equal to sigma by E, right? And we are directly applying the force in y direction. So E equal to sigma y by E for y direction. So here I have taken linear strain, a strain in y direction equal to Ey equal to sigma y by E, and strain in the x direction. Again, I am using formula mu, that is Poisson's ratio equal to lateral divided by linear. But in this case, linear strain equal to Ey and lateral strain equal to Ex and Ez, right? So just using this, mu equal to minus Ex divided by Ey, will get the formula Ex equal to minus mu into Ey equal to minus mu sigma y by E. And similar for the z direction, Ez equal to minus mu Ey equal to minus sigma y by E. Now third, due to sigma z, strain due to sigma z means we are applying the force in a z direction. Here force is a R. Now forget about these two, P and Q. Just concentrate on the R force and check the effect. If we are applying the force in a z direction, this breadth dimension is going to increase. Right? Means this is the linear strain because we are measuring the deformation in the direction of applied force. But whenever we apply the force in a z direction, at that time thickness is going to change, and there will be a decrease in a thickness, and at the same time there will be a decrease in a length also. Means this, in a thickness direction we will get lateral strain, in a length direction we will get also lateral strain. So for the strain in a strain due to sigma z, we can write in a z direction Ez equal to sigma z by E. Ez equal to sigma z by E, and similar to above, Ex equal to minus mu into Ez, and Ey equal to minus mu into Ez, or simply we can say minus mu into sigma z by E, right? Now, total strain, we need to calculate the total strain. So total strain in x direction, we need to do some summation of strain in x direction, summation of strain in y direction, and summation of strain in z direction, because simultaneously we are applying three forces. We are applying P force in x direction, Q force in y direction, and R force in the z direction. So there will be a three effect of each forces, right? So we need to do addition of strain in x direction, addition of a strain in the y direction, and addition of a strain in the z direction. If we write this all summation, strain in x direction, strain in the y direction, and strain in the z direction, finally we'll get that is strain equal to that is called as a actually volumetric strain. Okay, so for that purpose I have written here EV, volumetric strain, equal to sigma x plus sigma y plus sigma z divided by E into 1 minus twice mu. If we solve this all if we solve this equation, finally we'll get sigma x plus sigma y plus sigma z by E into 1 minus twice mu. So this is the volumetric strain. Okay, volumetric strain is nothing but the change in volume divided by original volume. Change in volume divided by original volume. EV equal to strain in x direction plus strain in y direction plus strain in z direction. So due to that, here we have added all the strain in x direction, strain in y direction, and strain in the z direction. And finally we will get sigma x plus sigma y plus sigma z by E divided by 1 minus twice mu. This is known as a generalized Hooke's law. Okay. Now here, if strain in a given in a two direction, stress is given or force applied in a two directions. Let the force acting in a x direction P and in a y direction Q, and if stress or force absent in a third direction, that is z direction. So here directly we can put sigma z equal to 0. We'll get the equation for the biaxial loading. If stress is applied in one direction, maybe in x direction or y direction or z direction, if stress is applied in one direction, we need to keep other stresses 0. Suppose stress applied in y direction only, stress not applied in the z and x direction, just put sigma z equal to 0, sigma x equal to 0. You will get the strain, volumetric strain. And this equation is important to calculate strain in a particular direction. Sometimes this formula is applicable to calculate the volumetric strain. Okay, but whenever we need to find out strain in the x direction, this formula is not useful. If we need to calculate strain in the x direction, this formula is not useful. At that time we need to prepare such a type of a chart, and then we need to calculate the strain in the x direction. Okay, so we'll solve one example on this. Here, a steel bar of a 200 mm long with 40 mm square cross section is subject to tensile stress of 100 Newton per mm square along the length and 400 Newton per mm square on the other lateral surface. Okay, resulting in a change in a volume as 120 mm cube. Determine the Poisson's ratio and total strain in a x direction. Total strain in a x direction. Take E equal to 2 into 10 raised to 6 Newton per mm square. Okay, so the statement is given. First we need to convert statement into a diagram. So 100 Newton per mm square stress acting in x direction, and that stress is a tensile. So it's positive, and in another direction stress is a 40 Newton per m square. So here another direction mentioned that lateral surface. So we can take in y direction or we can take in a z direction also. Okay. Result in a change in volume due to this application of force. Change in volume is a 120 mm cube. Change in volume is a 120 mm cube. Okay. Now we need to find out the Poisson's ratio, that is value of mu, and total strain in x direction means we need to calculate the value of Ex. Okay. Now you can see here delta V is given 120 mm cube, and to calculate the mu. Okay. First we will generalize Hooke's law, that is Ev equal to sigma x plus sigma y plus z divided by E into 1 minus twice mu. Now here this delta V is given, but we know that Ev equal to volumetric strain equal to change in volume divided by original volume. So change in volume is given 120 mm cube. We can calculate the volume of the bar, because it is 200 length is given and 440 mm square bar. So we can easily calculate the volume 200 by 440 into 40. Okay. And next important, that sigma x value is given 100, sigma y value is given 40, and both are tensile. So I have taken here positive sign, but there is no force in a stress in a z direction. So directly we can put sigma z equal to 0. Then value of E is given 2 into 10 raised to 6 Newton per m square, and we need to calculate the value of mu. Just putting the values, finally we'll get the value of mu equal to 0.29. Please keep in mind, value of mu is always lies between 0.10 to 0.50 only, and it is always negative value. Okay. So here we can easily find out the value of mu, but to calculate the Ex, calculate the strain in the x direction, we need to use this chart, strain in the x direction. Sorry. I will take this figure for the calculation purpose. Now in x direction stress is a 100, y direction 40. Okay. Now we need to calculate the strain in the x direction, means due to sigma x, Ex equal to sigma x by E equal to 100 divided by 2 into 10 raised to 6. Okay, 2 into 10 raised to 6. Into 10 raised to 6. Now we are not going to calculate strain in a y direction, z direction, but okay, so and we need to calculate strain in a we need to calculate strain in a x direction only. Now due to sigma y means strain due to force in a y direction. So due to force in y direction, we are applying the force in y direction, and we are measuring strain in the x direction. We are measuring deformation in the x direction, means again it's a lateral strain. So Ex equal to minus Ey. We know the value of mu and sigma y. We also know the value of E. So just we can put here value of mu 0.29 into value of sigma y is 40 and divided by E, 2 into 10 raised to 6. 10 raised to 6. Okay. Now in third direction due to sigma z, but there is a as per given statement, there is no force in the z direction. Okay, so in z direction, but sorry yes, we need to consider this train in a y direction. Due to sigma y, ex equal to minus mu into ey equal to minus mu ey by e. Now to due to sigma z, actually sigma z is absent here, so we need not to do calculation for this term. And we also need not to consider these two columns. So we need to focus on this only. Strain in the x direction due to sigma x and due to sigma y only. Because as per given statement, we need to find out ex, strain in the x direction only. So strain in x direction due to sigma x only, means due to application of force in x direction only, and strain in x direction due to application of force in a y direction only, right? So we need to consider only these two element due to sigma x in x direction, due to sigma y in x direction, and then we need to do summation for these two. Then we'll get the strain in a x direction. We can't use this formula to find out the strain in a x direction. To find out the strain in a particular direction, we need to prepare such a type of a chart. Means we need to consider strain in x direction, y direction, or z direction due to stress in x direction, stress in y direction, and stress in a z direction. Then only we can calculate strain in a particular direction. And generally in GATE exam, they ask strain in a particular direction only. Values are very simple. When this such a type, this similar problem given, and you need to calculate strain in x direction, y direction, or z direction. So you should be able to prepare such a type of a chart. This chart is there is a logical reason for each strain value, and you need to also check the sign. If here is the compressive force, meaning in y direction, if force is a compressive force, at that time this t dimension means here linear strain is a negative, but at that time lateral strain is a positive. Please keep in mind. Suppose force in a y direction is given in a compressive force. Let q be the compressive force, and that is the compressive force. Now this equation will change. In y direction, we'll see in strain in y direction. Okay, so ey, value of ey will be minus sigma y by e, because if we apply the compressive force in y direction, then that thickness is going to decrease. For the decreased dimension or contracted dimension, we use a negative sign. So strain ey equal to strain in y direction equal to minus sigma y by e. At the same time, this strain in the x direction, strain in a z direction will get the positive value. Will get the positive value because these strain are a lateral strain. When linear strain is a negative, at that time lateral strain should be positive. Okay, so in this way we can solve the problem on the triaxial loading. So this related to uniaxial loading, biaxial loading and triaxial loading. Okay, and sometimes we need to use these relations to calculate the another values, means value of k means bulk modulus is nothing but the direct trace divided by the change in volumetric strain, direct trace to the volumetric strain. And you know the E means modulus of elasticity, that is sigma by E. G is the modulus of rigidity, shear force, shear stress divided by shear strain, tau by 5, and mu is the Poisson's ratio, lateral strain by linear strain. So you need to remind this formula: E equal to twice G 1 plus mu, E equal to 3k 1 minus twice mu, and E equal to 9 kg divided by G plus K. So along this triaxial loading, biaxial loading, this elastic constant question may be accompanied. Okay, so you need to remind this formula: E equal to twice G 1 plus mu. These all are the elastic constant, because this is according to Hooke's law. E equal to sigma by E. This mu Poisson's ratio is also constant. G is a modulus of rigidity and K is a bulk modulus. Okay, so to solve the problem you need to remind this formula. So this is about the simple stress and strain. Whenever axial loaded member and member are in a series, then compound composite member means two different material connected together and system is in parallel. And third, that is generalized Hooke's law, or volumetric strain, that is delta V by V, or triaxial loading, biaxial loading, or uniaxial loading is given. And elastic constant. So this is about the simple stress and strain. If anybody having doubt, you can ask. If anybody having doubt, please ask. Just a minute, I will share the link. If you have any doubt, please put a message in the chat box. Please share this PPT for reference. Okay, so okay. Prachi, definitely I will share the PPT. Also, I will share the video also. I will upload the video on YouTube. And more problems also I will share. I have already prepared the PPT related to SFD, BMD, and the simple stress and strain. I will share. Definitely I will share. Please fill up the Google form. And whenever if you have any doubt, you can you can also WhatsApp related to any unit. Please fill up the feedback form. If you have done, you can leave the class. Thank you, Aditya.